All right, so for this problem, we have a source of fluid here, M, and it is releasing a fluid that is hitting our wall over here a certain distance away, which is our L value. So in this problem, it gives us our velocity potential function, phi, written here. And we can use this function in order to get our fluid velocities in the given directions that we need. So conceptually, what we need to know is that when we take phi and we derive it in relations to x, we get u, which is the fluid velocity in the x direction. And if we take the derivative in relation to y, we get the fluid velocity in the y direction. Same thing with z, fluid velocity in the z direction, and these are known as u, v, w. So for our part A, we need to show that there's no flow going through the wall. So we need to find u. So for u, it is the derivative of phi in relation to x. So we have our constant, m over 4 pi, and this constant, because it's positive, that's showing that it's a source and that water is going out. If it was negative, it would be taking fluid in. So our constant goes out in front, and we have two ln's that we need to take the derivative of. So in order to do this, all we need to do is take the inside of our ln, find the derivative of it, and multiply it by 1 over this value. So like for ln x, the derivative of ln x would be 1, which is the derivative of x, times 1 over x. So we're going to do the same thing here. So first, we'll take our derivative of this inside part, and the derivative of this is going to be, so it's simply just, let's see, 2, just bring that out front, x minus L, and we're going to multiply this by 1 over our original, so x minus L squared plus y squared. All right, we know the parentheses there. All right, so not too bad. There's our first ln there, and for our second ln, it's very similar. This sign change is the only difference. So it's going to be 2 x minus L times, excuse me, I believe 2x plus L times 1 over our original, x plus L squared plus y squared. Okay, great. So got that, one more parentheses. So now simplifying this down, we get u equals, so this simply goes to the top, this simply goes to the top. So it's going to be, so 2x minus 2L over original x minus All right, so now that we have this, we have successfully found our u. That's great. So now all we need to do is substitute our x value in. All right, well, where are we looking? So here's our axis, here's our x-axis, here's our y. So we're focused on this point right here. So we know that it's hitting the wall, and when it hits the wall, x is 0. So we're trying to show that there's no flow through the wall right here, x equals 0. So all we have to do here is, this is 0, this is 0, this is 0, that's 0. So these all cancel, or they don't cancel, sorry, they turn to 0, they disappear. So that disappears, and that gives us negative 2L over negative L squared plus Y squared. Okay, great. Now we're moving on to here, plus 2L over negative L squared plus Y squared. So as we can see, we still have some variables in here that we could look at, but if you look closely, it doesn't matter because they're exactly the same. It's negative 2L plus 2L. So those cancel out and they equal 0, which shows us that there's no fluid velocity at our point here against the wall. So this shows U equals 0. There's no flow through the wall, of course. So now what we have to do, part B, it says determine the velocity distribution along the wall. So, all right, so what are we looking for? So along the wall, the velocity is being distributed up and down here. Okay, great. So we need to find V. So V is derivative of phi in relations to y. All right, so similar process. We're going to do m over 4 pi, and now we begin taking our derivative of these two ln's in relation to y. So if we're taking the derivative of this in relation to y, these two values are both constant. So when you derive a constant, it goes away. So y is our only variable we can derive here. So the derivative of y squared is simply 2y, so 2y over our original, once again, all right, plus, and then once again, another 2y over x minus L squared plus y. All right, great. Oh, and excuse me up here for not writing m over 4 pi. This should be somewhere in here. M over 4 pi, just noting that. All right, so we have this. Now what we can do is we can simplify it some more. M over 4 pi once again. Now our the bottom part's the same, so this simply turns into 4y over x minus L squared plus y squared. All right, so now we can see that our 4's cross out. So we are left with V equals m over pi. Here's our y over, and then for our x here, our x value is 0 once again, and yeah, our x value is 0 once again because along the entire distance of our wall it's 0. So this way it's x is 0 throughout the whole height of the wall. Of course, makes sense. So once again, we're gonna write negative L squared plus y squared, and this gives us our V value. So our velocity against the wall can be found at this function. And so for this, what we can do here is we can plug in different distances of our source, where our source is actually coming from for L, and our height y right here at any point along the wall, and it will tell us our fluid velocity at the given point. So we can take it here, it doesn't matter. All right, so that is our velocity distribution along the wall. So now what we need to do, our part C, it's asking us to determine the pressure distribution along the wall. All right, so we found our U, we found our V, but when we need to correlate pressure into this, we need to use Bernoulli's equation. And so Bernoulli's equation is as such. All right, so we have Bernoulli's equation here. Now we need to make some things, we need to do some things with these variables and actually tell them what they are. So we know in this example, our z's are equivalent. So those z1 equals z2, so those will cancel out for us. Our v1, we are going to relate to our u for x, and that is going to be 0, so that goes away. So we're canceling things out. In our problem, it shows us that P equals P naught, so we're going to change that. So P1, which would be our P, equals P naught. Excellent. And now our final thing to do is our P2. Actually, wait, this isn't our final, I'm sorry. Our P2, so for this side, we're going to relate this to our vertical on the wall. So P2 is going to equal pressure on the wall. And our V2 is going to equal our velocity on the wall, which we found in part B. So we'll be bringing that in a little later. All right, so now we can rewrite this whole thing with our given variables that we need while also canceling these out. So let's see. So P naught over and if we simplify this teeny bit, we get P naught equals these things times the specific weight, pressure of wall, that, those will cancel out later, velocity against the wall, 2g. All right, so now we can simplify this once again. So we're just gonna write P naught equals, so our pressure against the wall is isolated. Let's see, we're gonna have to flip these around a little later, but that's all right. So we're taking our specific weight and we're timesing it by this variable, but specific weight over G is going to simply be rho. So we'll imagine, so it'd be plus 1/2, that's accounting for this 2, and the rho is going to be that over our gravity, so there's rho, and then simply times velocity against the wall squared. So now that we have this, we can come back here with our V value and plug this in. So Actually, we're not quite ready for that. We need to switch this over to get pressure of the wall equals P naught minus 1/2 rho V wall squared. All right, now we can plug in our V. So we're gonna go pressure against the wall equals P naught minus 1/2 rho, and then we're going to take this value squared. So m over pi all right, excellent. There it is, inputted into the equation. Now we can reduce this a little bit more. So P naught minus 1/2, we're gonna distribute the square. So m squared over pi squared. Forgot about our rho there. So it's simply y squared over L squared plus y squared squared. All right, so now that we've distributed these squares across, we have our final answer for the pressure distribution along the wall. So pressure distribution along the wall can be found by using this. All right, and that is our final answer. I will write my signature here. Here I am, and that'll be it.